Okay, thank you, Olivia. Yeah, so I'm going to talk about Donaldson-Thomas invariants of threefold flops. Yeah, so I've tried to, I don't quite know who's attending, but I figured most people here know a bit about minimal model program, sort of birational geometry. So I'm just going to quickly recall a bit of that and then sort of go into the meat of flops and their invariants. Right, so quick recap. So in the minimal model program, we want to find good representatives of varieties up to birational equivalence. So the usual idea is you take your, say, smooth projective variety, do some sort of birational modifications to it, and find some sort of minimal representative in its birational class. Right, so if everything goes well, you'll end up with something called a minimal model. So that's a variety in which every embedded rational curve has positive intersection with the canonical bundle. So that's the NAF condition. Right. So it's sort of the classical result of the Italian school that such minimal models exist for surfaces, and they're also unique. But as soon as you move to dimension 3, they might not be unique. They do exist, with some exceptions, but there are finitely many. And these finitely many minimal models are connected by some further birational maps called flops. Right, and flops also exist in higher dimensions, but the existence of minimal models is a bit more conjectural there. So today we're going to talk about dimension 3. Right, so the picture to keep in mind is the following. So there's some curve inside our threefold, which has a trivial intersection with the canonical bundle. And this is our flopping curve. Such curves are contractible. So there's some map down to some other variety with a singularity, which is the image of our curve. And there's another way to, so this is a blow-up map, and there's another way to blow up, and this gives you a new variety with another curve. And so in general, there's going to be multiple curves, and these minimal models can have some singularities. In fact, to run the minimal model program, you need to allow for some singularities. But today we're going to keep it simple and just talk about simple flops where the space is smooth and the curve is just a single rational curve, so just a copy of P1. Right, so this sounds sort of like a very simple picture, but in fact this has some very interesting geometry, and it's sort of a local geometry which we care about. So we're just sort of interested in some area around the singularity and its blow up. So some neighborhood, which might be some open neighborhood or some formal neighborhood or something of the sort. And it turns out that these spaces and the structures on them have some interesting deformation theory, and this deformation theory yields all kinds of invariants for us, and that's what we're going to study today. And most of these invariants will come from some sort of physics motivation. There's all kinds of field theories which are related to these spaces. And in particular, they're Calabi-Yau threefolds, so there's some sort of string theory connection. Right, so like I said, we're going to look at smooth neighborhoods of flopping curves. It's usually useful to work over some sort of affine base, so some small neighborhood. Right, so these are called simple flops. Right, so what do these look like locally? So we have our neighborhood, we have our P1, which we're contracting to a point. But in fact, if you look at the fiber of this point, then this has a non-trivial, non-reduced scheme structure. So it's not just a P1, it has some sort of multiplicity. So basically what you do, you pull back the maximal ideal of the point, you get some ideal sheaf, and the powers of this ideal sheaf give you a whole chain of subschemes, ranging from the fiber to our P1. So we have our curve, some first thickening, and so on until you get the full thickened fiber. Right. So although there's only one curve in the picture, actually when you start studying these spaces, there's all kinds of different curves showing up, non-reduced curves. Right, so the first question you might ask is, well, how many of these curves would there be? And that's an invariant called the length of the curve. The options of this length were classified by Katz-Morrison in the 90s. And they're related to ADE singularities. And therefore we get a very nice finite classification. So the length is an integer between 1 and 6. If it's 1, you just have P1 as your fiber, and if it's 6, you have something very complicated and intricate. And there's a lot of stuff in between. Right. So people start looking at these flops and try to classify them. And in the simplest case, you can just completely classify them. This was done by Reed in the 80s. It turns out that there's just a single family. There's just a single integer that completely classifies all these flops with length invariant 1. Right. So what can we say about the other ones? As I mentioned, this is sort of the easy case, and the rest is significantly harder. And in fact, we don't have a good classification of all these other guys, only some examples. So the natural thing to do is to start studying invariants of these spaces. And well, this integer invariant that Reed used to classify the length 1 flops can be generalized to something more intricate. So these are some invariants that come from string theory, or well, they're motivated by string theory at least. These are called Gopa-Kumafava invariants. So the story goes is that the Gromov-Witten theory of Y, so the curve counting of the space, is controlled by a finite number of integer invariants. And you get one integer for each of these curves I just mentioned. So there's a curve count in a way for each of these non-reduced subschemes between the curve and the full non-reduced fiber. Right, so these are just some sort of multiplicity. There's a formal way to define them, but I won't do that here. Right, and as I mentioned, this is a generalization of what Reed did, because in the length 1 case, you just have single invariant, and that's just the one we use to classify this family. Right. So you might ask, with these new invariants, can we completely classify curves? Can we completely classify flopping curves? And the answer is no. And it's a very recent answer by Brown and Wiens. So they show that there's multiple non-isomorphic flops which have the same GV invariance. So if we want to approach this classification, we need something stronger, some sort of other invariance. And so that's what this talk is about, is sort of exploring what we can say if we start looking at other invariants. Right. So if we want to generalize these GV invariants further, then we need some sort of more general theory. So it was shown by Katz at the start of the millennium that these GV invariants are examples of Donaldson-Thomas invariants. So they're some sort of virtual count of sheaves supported on the curve. So this is some Euler characteristic, virtual Euler characteristic of some moduli space of sheaves. Right. That's a bit vague, of course, but that's the idea. But the thing is that DT theory can do more than count just these particular sheaves of these particular classes. We can, in fact, look at all kinds of other moduli spaces and try to count more sheaves. So the question is, what can we find if we start sort of taking this seriously and look at the complete picture? Right. Right. And so the complete picture extends into two ways. So we can extend our invariance. We can just look at more classes. So if we look at the K-theory of compactly supported sheaves, with support on our curve. So that's basically just a K-theory of the curve itself. So given by a rank and a degree. Then we can define invariance for every choice of rank and degree. And these GV invariants will correspond to specific choices of classes. Right. So in general, we can define DT invariants, which will be some virtual counts on some moduli space of objects supported on the curve with this specific class. And when I say objects, I mean objects in the derived category of the space. Right, and this will recover the GV invariance. That's another result. So this is like a natural generalization. But it's not entirely clear how much more data this will actually add, if there's actually any new geometry captured by these invariants. So that's a bit of an open question. Right, and the second thing we can do is to refine the invariants. This is sort of a prediction by Kontsevich and Sogelman that these DT invariants, which count points on a space, should behave a bit like, well, a measure, a constructible measure on the space. So they should be motivic, which means that these invariants should be able to lift to some sort of more interesting ring of motives or mixed Hodge structures or something like this. And this is something that has been developed in later years, but it does require a bit of extra data. So you need some sort of deformation theory data on your moduli spaces. And so part of this refinement is that you need to take care of this extra data and sort of work with it and see that everything works out. Right, so some calculations for flops have been done in this full extended and refined setup, but only for the very simple cases of length 1 flops. So the family of length 1 flops has the TF flop as the first entry. It's like the also called the conifold singularity. So that was done by Morrison, Muscovy, Nagoa, and Sendroy, and all the later cases were done by Devs and Meinhardt. Right. The thing is that their calculations use like a very nice setup. These length 1 flops are just very well behaved, and we just know very well what their moduli spaces look like. But as soon as you start going to higher lengths, this becomes quite difficult. And so if we want to understand the moduli of sheaves on these spaces, we really need some sort of grip on the stability conditions on the space and also on the deformation theory of the objects supported on the curves. Right. So I guess I'm gonna make a quick sort of setup of the sort of stability conditions. To be fair, I'm just gonna butcher the subject a bit, but I'll tell you sort of the idea why we use stability conditions for DT theory. So I guess it comes down to this problem of counting moduli of objects. There's a lot of objects in the derived category, even if we look at just the complexly supported stuff. And in general, because these are threefolds, everything's very, very wild, basically. So you have no hope of actually classifying what all the objects are. Describing moduli spaces is very difficult, but you can break them down into more manageable pieces if you find some sort of way of filtering your objects. And that's where the stability conditions come in. So the idea is that you want every object to have a unique filtration by some manageable set of objects, which we call the semistable objects. Right. So I'm going to use Bridgeland stability conditions for this, which more or less come down to choosing an abelian category inside your derived category, for which it is the derived category, so the heart of a T structure. And then an ordered set of semi-stable objects. So we order them by some phase, so some real number. And for every real number, there might be a set of semi-stable objects with phase phi, which most of the time is empty, but this gives a linear order on these semi-stable objects. Right, and then we ask that this data, so these hearts and these semi-stable objects, satisfy the Harder-Neresimon property. So every object in this Hart should have a unique filtration with subquotients given by some semi-stable objects, and the phases of these semi-stable objects should be ordered according to the standard order on the interval. Right. And in doing this, if your category is nice and you have like nice moduli spaces to begin with, then this will give you a stratification of the moduli space by the type of filtrations you get. So you can decide for every object what type of phases occur in its filtration, and then this gives you some sort of constructible decomposition of your moduli space. Right, and so that that breaks down the problem immensely. Right. Yeah, so that's this formula, I guess. Right, and so there's been a lot of work on interpreting this in DT theory. So if we want to count objects on here, then we can look at each of these strata. And because these strata are well, given by extensions of semi-stable objects, so objects which filter by certain semi-stable objects, we get a nice formula in DT theory. So that's the wall crossing formula. And so, yeah, okay, quick disclaimer. So you need some sort of extra conditions on your category. But if you're nice and 3 Calabi-Yau and all that sort of good geometric, if you have all those nice geometric properties, then you'll get a formula along these lines. So we get a generating expression for the DT invariants. So the power series with coefficients given by the DT invariants is generated by some invariants called the BPS invariants, which only need to be calculated for every semi-stable object. So the total counts of sheaves are controlled by some smaller amount of data, which is captured by these semi-stable objects. And to relate it to, there's some sort of exponential, which is like a bit of a headache to deal with, but this is sort of the standard technicality. Right, so that's the takeaway, is that if we have such a stability condition, which has this Harder-Neresimon property, then we get our nice decomposition in DT theory. So we know, if we know about the moduli spaces for every class of every semi-stable object, then we can calculate this and we win. Right. So the only thing that remains is to actually understand the stability conditions for our flops. Right. And that's where we start doing tilting theory. So tilting theory is a way of systematically understanding what these stability conditions will be. Right. So the definition of a tilting bundle is as follows. We take a vector bundle on our space. Then this vector bundle is tilting if it doesn't have any higher self-extensions. So its anamorphisms its derived anamorphisms in the derived category are just the normal anamorphisms on the variety. And additionally, we want that T to generate the derived category under triangles, so under extensions and subobjects and that sort of stuff. So what this condition gives you is a way of rewriting our derived category of our geometry into the derived category of an algebra, some sort of non-commutative algebra. So there's a derived equivalence given by this tilting bundle from coherent sheaves to modules of the anamorphism ring. And if we look at compactly supported stuff, then we'll get finite dimensional modules. Right. And there's a few benefits to working with these non-commutative rings. For one, there's just more techniques that apply to non-commutative rings. But there's also some sort of intrinsic property of module categories or rings that are very useful, especially for stability conditions. So finite dimensional modules of a ring form a length category, so they have Jordan-Hildreth filtrations, which means that filtrations in this category are much easier to deal with, and we know that they exist. So it's easier to define stability conditions in this sort of setup. Right. So in case of flops, so again, I'll do this for simple flops. The existence of tilting bundles was shown by Vandenberg at the start of the millennium. And the anamorphism algebras of these tilting bundles, which will be decomposed into two summons, will be some sort of quiver algebra. So in the length 1 case, this will look something like this. So we have two vertices, one for each summand, and then arrows between them corresponding to the homomorphisms between the two summands. And then there will be some complicated relations. For higher lengths, these will look something like this. Again, two vertices and some arrows. Right. So instead of studying the geometry, we can study these quiver algebras. And that's often very useful. Right. And in general, if you start looking at flops with other curves or flops with extra singularities on Y, you'll get more complicated stuff. So if you add a curve, you add a vertex in the quiver, and also extra arrows and relations, and everything becomes more complicated. Right. So this is one tilting bundle, which gives us one such algebra. But in fact, there are many such tilts, and many of these non-commutative rings which are equivalent to our geometry. And yeah, classifying what all these different tilts are was done by work by a lot of people. It's sort of based on this work on non-commutative graph solutions by Yama, which my supervisor worked on with a lot of people to completely work out for flops. Right. And so if you look at all these tilting bundles together, they form a very nice structure, which is some sort of wall and chamber structure. So it's something like the following picture. So this picture is the K-theory of Y, or the K0 of the perfect complexes. And it gives you chambers and walls. The walls are the K-theory classes of the summons of the tilting objects, and the chambers are well, correspond to the tilting objects made up of the two summons of the walls. So here we get a tilting object T0 plus T1, here T1 plus T2, and you can keep going like that. Right, so yeah, they form this nice dense picture separated by these walls, and then there's this this sort of limit wall in red, which doesn't correspond to any summon of any tilting object, but it's like an accumulation ray for all these hyperplanes. Right. And so for every chamber we have a tilting bundle. It's anamorphism algebra, so some sort of quiver algebra. And then the finite dimensional modules over that give us some abelian heart of some T structure in the derived category. And yeah, these different hearts are related by functors, by some sort of mutation functor. And so that's if you cross a wall, you do a mutation, and if you flip the diagram, you do a duality, which more or less corresponds to actually doing the flop, though sort of hard to see that in this picture, right? So having these hearts and all these chambers gives us one part of the stability conditions. The second part is defining some sort of phase and defining what the semi-stable objects are. Right. Well, there's multiple ways of defining stability conditions. Usually one chooses something like a central charge, but in this case it's easier to use something more akin to slope stability. But more specifically, we'll take pairing between our classes in this Wallen chamber structure and the classes of our modules. Right, so we have the actual K-theory and the algebraic K-theory of the compactly supported objects. And we pair these into the K-theory of C using the home functor. Because we're using with derived categories, you should take the derived further. Right, and because this is sort of a real picture, we realify the K-theory and we'll map into the reals. Right, so if we take any class in our K-theory, we get a linear map on the classes of the finite dimensional modules. So we can define some sort of phase function which maps a class to its inner product with a K-theory class, and then do some sort of monotonic thing to go from the reals to the actual interval, which I won't bother on. Right, so we have some sort of phase, and then we can give the actual condition. So an object is semi-stable if every sub-object has a smaller phase than the phase of that object. And so everything that satisfies that property is semi-stable, and then we decompose all the semi-stable objects by phase into different sets, by just decomposing them. Right. So because we're working with a length category and all these filtrations are nice, we always get this Harder-Narasimhan filtration. So that's good. That's what we want. So we get our nice DT formula. And moreover, every one of these guys is an abelian category on its own. And it's also a length category, so there's a Jordan-Hölder filtration in every one of them. So every object in there is also an extension of some sort of smallest, relatively simple object. And those objects are called the stable objects. Right? So we can already find two of those stable objects for each choice of heart. So if we look at this anamorphism algebra for one of these chambers, then we have two simple objects. So we have a quiver algebra with two vertices. Every vertex has an associated simple module, which is just the one-dimensional vector space supported at that vertex, on whichever arrow acts trivially. And that has no sub-objects, so it's automatically just going to be stable. Right? And this is sort of orthogonal to the summons of the tilting object. So the projective covers of these simples are the images of the summons to which they correspond under this tilt. Right. And as I said, the classes of these guys span the walls in this wall and chamber structure. So this wall will be orthogonal to the simples in this heart. So we get some sort of duality between these guys. All right, and so the thing is, when you start mutating, when you start moving from heart to heart, these simple objects get sent to other modules. And it turns out that when you do this in the correct way, you actually keep these modules actually stay stable. And so you obtain a whole string of stable objects by comparing stuff in one heart to the other. And so one of the theorems I proved is that this is actually all you get. There are no other simples, simples which are dual to this extra accumulation rate. Right, so we have semi-stable objects for the simples, and their extensions. So these guys are dual to this ray, and then you get more semi-stable objects for stuff that's orthogonal to this ray, and so on and so on. And that completely gives you all the stability, all the semi-stable objects in your gallery. Right. So that's great. That's the full picture. So everything is obtained as some sort of stable or some sort of simple and some hard. And it turns out that by chance, these symbols were also recently classified by my advisor and one of his collaborators. And so they're going to correspond to points, which have a class that's orthogonal to this accumulation ray. So they're like the one special case I mentioned. Then there's the structure sheaves of the curves, and there are twists and shifts in the derived category. Once you start going to the more complex cases, there's some sort of exotic stuff showing up, some extension between these guys as well. And so what this means is that so the stability is completely captured by points and curves, and therefore the DT theory is also controlled by points and curves, point counts and curve counts. Right. Gives us the whole picture of our extension to more classes. If we want to know about the DT theory, we only need to count points and we don't need to count curves. So then the second point is to refine these invariants, so to add in the deformation theoretic data and see what sort of motivic invariants or Hodge theoretic invariants we can extract. And so these invariants depend on potential, which encodes this deformation theoretic data. The picture to keep in mind is something like this. So we have some sort of moduli space. Points on the moduli space correspond to some compactly supported objects. So some sheaves or some shifts or complexes of sheaves. And each of these guys has a deformation theory captured by the extension algebra, which has some sort of A-infinity structure, which expresses the deformation theory. And moreover, because we have a Calabi-Yau manifold or a Calabi-Yau variety, these algebras also come equipped with an inner product. And by combining this data, we can encode this A-infinity structure into some sort of function, some non-commutative polynomial or power series. And that's called the potential. Right. So that's just some formal machinery, and we can compute this potential in certain cases and only in certain cases. So if we want to work with this sort of extra data, then we should see if we can sort of reduce to cases which we can handle. And since we've been doing all this tilting business, going from hard to hard, and applying all these functors all over the place to get our stable objects, if we want to compare the deformation theoretic data of these different objects, then we should see if this is preserved by these functors. Right, so first is some good news is that these tilts are a type of Morita equivalence, and this all works perfectly fine with the A-infinity structure. Once you take some sort of enhancement of your category, so that's good. But there's also the second part, which is this inner product. So this Calabi-Yau type structure, and it's not entirely clear that this is preserved. So it turns out that the thing to track, to check that this is all compatible is something called a Calabi-Yau structure, which is a map from the Hochschild homology of the compactly supported objects into the base field. So this determines some sort of class of such a product, and there's some sort of perturbation theory you can do to show that if this class is preserved by your tilting, then you can make it all compatible. Right. So to check that we can actually preserve something like such a class, we again use this pairing on the which we define on the K-theory, but now on Hochschild homology. So there's a pairing again from the home functor between the Hochschild homology of Y and the Hochschild homology of the compactly supported objects on Y into the base field. And this gives us pairing between these Calabi-Yau structures, so these inner product pairings, and volume forms on Y. So some sort of isomorphism between, or well, some choice of section of the canonical bundle on Y, and yeah, keeping track of this inner product, which is a bit of a headache, can then be done more easily by checking that the tilting functors preserve this Calabi-Yau volume form. Right, and so that all works out because this pairing between the Hochschild homologies is invariant when you apply the tilt on both categories. And so, yeah, so we find the following theorem. So if we have some sort of tilting functor f, then this has an action, functorial action on the Hochschild homology. So if that is trivial, so trivial or maybe up to a scalar, then this functor also preserves this inner product and therefore the potential that the A-infinity structure and this inner product define. So you get the same potentials for an object and its image under the functor. And again, if this is not quite trivial, but there's some sort of scalar, then you can just multiply by some scalar instead. Right. And in either case, this scaling of the potential or this invariance of the potential means that the counting invariance we get for both objects are going to be the same in the refined theories. Right. Right. So that's the second theorem I proved in my thesis, is that this tilting is also compatible given this condition, and therefore the refined theories also behave nicely with respect to this tilting. Right, so that was a bit abstract maybe. So I'll talk about the implications it has. In the first new case of flops. So like I said, the length 1 case was already studied before. And we already know that these are classified by like the integer invariants. So let's see what happens once we go to length 2. Right. So we have a whole host of examples. We don't quite know if it's exhaustive. First were constructed by Laufer in the 80s and some by Pinkham. then recently by Brown-Weems and by Kawamata this year. So this will be our subject. So we can explicitly calculate all the invariants for this family now. Right. So first, we know what the stability is. So from the first theorem, we get that the stable objects are points, curves, and the thickened curves. So this is the structure sheaf of the scheme fiber, and this is of the curve. And then there's some twists and shifts. And from the second theorem, we get that these twists and these shifts also preserve the DT invariant. So these twists and shifts are sort of the geometric version of this of these tilts. Right. And so the implication is that the DT theory is completely generated by point counts and curve counts. So we get some sort of generating expression for the DT theory in terms of rank 0 invariants, so point counts, and then curve counts of rank 1 and rank 2 curves. And then we also need to worry about or count points on the moduli spaces of extensions of these guys as well. So there's there's still infinitely many invariants, but there's only 3 classes to worry about. All right. Yeah, so that's sort of the takeaway is that everything is determined by points and curves. But once you start actually calculating stuff, then more is actually true. So up to a certain level of refinement, which is the harsh theoretic one. So sadly, I wasn't able to completely calculate all this stuff for motivic invariants. But the thing you find is that actually most of these invariants vanish. And the invariants of this this fiber are also just the invariants of the curve itself. So actually, once you start calculating everything, there's only 3 invariants left. So there's the count of points, count of rank 1 sheaves, and count of rank 2 sheaves. And these correspond nicely to the 2 GV invariants, which we talked about earlier. So we do some refinement of these guys, but ultimately the GV invariants determine pretty much everything in the DT here, except for these curve count, these point counts, which well, this is sort of boring. These are the same for every floppy lookup. Right. So this statement that these refined invariants, these specific refined invariants completely determine the DT theory is part of a conjecture, or a refined version of a conjecture by Pandharipande-Thomas called the strong rationality conjecture. So you can actually verify that this holds in these cases. All right, so this is kind of I guess it's a kind of a negative answer to sort of the aim of extending our knowledge by calculating more invariants, because it turns out there aren't really that many more invariants. up to equivalence. So yeah, the next thing to do is to look at the refinement. Maybe by calculating these more intricate invariants, we can find something, find something more. And it turns out that actually we do get something very, very interesting things to show up. I've given the motivic invariants here. So we have the point counts. So the point counts are just the points on the variety. So they'll give you some sort of motive of the variety as an invariant. But the more interesting ones are the curve counts. So the counts of the rank 2 curves will be some expression involving the Lefschetz motive, so the motive of the affine line, and some sort of motive of roots of unity, and these come with monodromy. What's more interesting is the counts for the rank 1 curves, which also have this monodromy, but it acts now on some sort of genus A curve, so some actual geometric object which has a non-trivial Hodge structure with some sort of action on its middle, on the middle part of it, right? So this is sort of very intricate, and this monodromy is a bit mysterious where it comes from, but it's not quite enough to actually classify flops. So for this specific family, all these invariants only, so this is a family in 2 parameters, which are both some sort of integers, but the invariants we find only depend on one of them. And so we can find examples of flops with different parameters, which are non-isomorphic, which have these same invariants. So even doing all this refinement, we still can't determine flops, which is, well, I don't know, it was a bit of a surprise to me, but I guess it tells us that there's something is still lost when doing these calculations. This DT theory just can't see the complete geometry, or can't really express the complete geometry. Even if we're just looking at like a curve in some space, its deformation theory is just too complicated to be captured by these invariants. And the only alternative that I know of is to look at the non-commutative deformation theory, to use something like contraction algebra invariant, which is some sort of non-commutative finite dimension algebra. But yeah, that's a completely different story. So I'll leave it at that.